Hello guys, so today we are here to solve our lead code challenge reverse odd levels of binary tree. In this problem we are given a binary tree which is not just an ordinary binary tree, it is a perfect binary tree. Okay, this is a perfect binary tree, and in this binary tree we have to reverse the node values. So please notice that we have to reverse the node values. We don't have to reverse the node. We have to reverse the value contained in the node at each odd level of the tree. So here 5, the value 5 is there on the right child and value 3 is on the left child. So when we reverse, 5 will go to the left child and 3 will come to the right child. So as a result of this reversal, the final you know uh, arrangement in this tree will be looking like this. Okay, so this is the initial arrangement and this is the final arrangement. Okay, now suppose the node values at level 3. Okay, okay, so it's saying that, see, this is the 0th level, this is the first level, this is the second level. So at third level, this is the values. Okay, so see, at third level it means there are in total 8 values. Okay, so this is coming from one parent, this is coming from the second parent, this is coming from the third parent, and this is coming from the fourth parent. And the parent of these nodes are sibling, and the parent of these nodes are also sibling, but these are the parent of these nodes are cousins of these parents. Okay, and parent of these nodes are the cousins of these parents, the parents on the left. Okay, so see, it is mentioning that this one is getting you know exchanged with this one is getting exchanged with this 29. Okay, and so like that this exchange is happening. Okay, and then finally we have to return the root of the reverse tree. Okay, so finally we have to return the root of the reverse tree. So see here, if we take this example, this one is getting, so whatever is so this is the left, the far left is getting exchanged with far right. Okay, so just like when we reverse an array, far left will be reversed with the far right, second far left will be reversed with the second far right, and like that this thing will be happening. Okay, so if we do it like this, okay, if we do it like this, then it should be coming like this. Okay, so let me just uh, go into the problem solution. So as a first step to solve this problem, if root is equal to null, okay, then we will return the root as it is. Why? Because since root is null, we cannot do any transformation on its child. Okay, so when root is null, we cannot do any transformation on its child. If root is not null, then there is a scope of transformation to be happening, there is a scope of reversal to be happening. And in order to do the reversal, we'll be calling this reverse method, and in this reverse method we'll be passing the two trees. These trees are the subtrees of the root, and these are root dot left and root dot right. Okay, and then will be this root dot left and root dot right. So these are at the level 1, so we'll be passing their level, and this method call at line number 19 will be happening after line number 18, and line number 18 is basically a check if root is equal to null or not. So if root is not null, then only we are hitting line number 19. If the root is null, then line number 18 is sufficient enough to handle that case. but if the root is not null, then only we are coming to line number 19. And this line, this function call is responsible for making the changes on the uh, root node. After the making the changes, we'll be returning the root. Okay, and then we'll be closing this out, and then private. So this reverse method is going to take the two childs of the root and perform the transformation. And since this tree is on the heap, whatever transformation is happening, it is going to be reflecting on the heap. And since that heap is accessible from both the methods, we don't need to return the anything from the reverse method, because whatever transformation is happening, it can be accessed from the first method also. Since the root reference is referring to the root node of the tree, that transform tree is still accessible from the first method, so we did not return anything. We'll just write reverse, and then in the reverse we'll be passing, we have been passed the two children. So one is left child and other is right child, and then we have also passed the level of the tree. Okay, now in this case, after the level of the tree has been passed, we will do if left is equal to null. Okay, so now one thing to be to be aware of in this case, it is mentioned, if you see here in this definition of perfect binary tree, it is mentioned a binary tree is perfect if all parent nodes have two children. Okay, so the possibility of a parent node having single child is ruled out by this definition. The perfect tree has to have two children. Okay, and all leaves are on the same level, all leaves are on the same level. Okay, so if a node is leaf on a level, then by the force of this definition, all the other nodes are also going to be leaf nodes in that level. So if we have checked if left is equal to null, then the other node right also, because the left and right, they are both on the same level. So if left is null, right will also be null. If right is null, then left will also be null. So we need not put a check like this. Okay, that and right is equal to null. This is not required. If one is null, the all others at that level are going to be null. So in that case, we'll be returning, and since we are not returning anything, so returning void, so we return method will just return without returning, just it will just return, it will just transfer of control will be happening, not a value will be returned. Okay, and then we'll be checking the level. Okay, if level is even or odd, so we can check this very successfully using this method is equal to 1. If it is 1, then we will store the value of left. Okay, left dot val in temp, and left dot val will be taking the value of right dot val. Okay, and then right dot val will be taking the value of temp. Okay, and then now the actual work of recursion is is understanding what call we are going to make. Okay, so this is handling the first level. Now we have reached the second level. Okay, so in this level, the pairing will be happening of this node with this node, and this node will be paired with this node. Why? Because if you see here, the far left is being exchanged with the far right, and then subsequently it is being exchanged in this manner. Okay, one is getting second far left is being exchanged with the second far right. Okay, so like that this exchange is happening. So the pairing in this case will be happening left dot left. Okay, So left dot left is this node and right dot right is this node. So right dot right is this node, and then level is level plus 1. Okay, and then reverse is again called left dot right. So left dot right is this node, and this will be paired with this node. 13 will be paired with 21, so it will be right dot left, and then same level will be level plus 1. So after doing this recursion call, we need not do anything else. Okay, and we will just run our method. Okay, my goodness, how it got returned. So as we can see, this is working fine. So let's submit this. Perfect. So there is one more way to solve this. Okay, instead of passing the level, what we can pass, since this is handling the case when root is null. If root is not null, then we are coming to the first level, and first level is an odd level. So we will be passing this value true, and we can pass the value true here, and the boolean will be boolean is odd, like this. Okay, and then in this we need not do all this. We can just check is odd is true or not, and if it is true, we'll be doing that logic, and for the next level we'll be passing not is odd. Okay, and same thing we can do here as well, not is odd. Okay, so this will also work. Let me just run this and show it to you. Not working. Why? True is odd. Oh, not is odd. You have to pass, because the next level is going to be an even level. That's why we have to pass not is odd in both the calls. Okay, if you are just passing in a single call, that is a mistake. So we have to be consistent in our logic. And let's submit this. So this is this is equivalent. I mean to say both these formulations are equivalent, and they are going to give the same result. The time complexity may be the implementation. This implementation is little slower because I think the JVM prefers handling the numbers, but it's okay. Idea wise, these two are the same, equivalent formulation of the problem. Now we will, the way I solved it in the first time was not using this. The way I solved it was using breadth first search, and in order to do breadth first search, what I did, that I used the queue. Okay, so if root is null, then we are returning. Otherwise, what we are doing, we are taking a deck of tree node. Okay, and this is deck is equal to new array deck. Okay, deck is new array deck, and then what we will do, we will offer to the deck.offer last the root node. Okay, and then we will be entering into this deck.is empty in this while loop, and in this while loop will be continuing till deck is not empty. Okay, and in this case what we will do, that we will take the size of the deck. Okay, and here only we will be declaring one level, and level is equal to 0. So at this level, when only we have the root, so the level will be obviously 0, but once we enter into this loop the level will be 1. Okay, and then here we are declaring one list of tree node. Okay, list is equal to new array list. Okay, and then for loop will initialize int I is equal to 0, I less than size plus I, and in this case what we will do, so this we can initialize here itself. Okay, and here we can do list.clear. Okay, and because this for loop is processing the loops in a level, the nodes in a level, and before processing the nodes in a level we want to clear the list. Okay, so what we will do here, that we will we will check, we will pull the deck. So deck dot pull, this will pull the element from the front of the deck and put it into the node reference. That reference will be stored in this node reference, and we can check if node.left is not equal to null. If node.left is not equal to null, then what we will do, that we can do deck.add deck.offer last. Okay, node.left, and the list will also be adding the node.left, and second if will be for the right child of the node. So if node.right is not equal to null, then the same thing will be happening, deck.offer node.right list.add node.left. So with this we will finish our for loop, and after finishing the for loop what we will do, that we will check. What we will check? We will check whether the level is so two things we can check. If it is possible that the left child and right child are null, we have hit the we are hitting the last level, so in that case the list could be empty, and we only want to go into this method, the method which you are going to reversal method, when the list is not empty, and level is odd. So when the level is odd, so in that case reverse will be called and will be passing this list. Okay, and after this we are going to complete this reverse method afterwards, but after this reversal the while loop is finished, will be returning the root, and so this will complete this reverse odd level. Now we have to write the private void reverse. Why we are not returning anything from the reverse? Because we are passing this object reference, and this object is actually stored in the heap. So this reference is pointing to the object stored on the heap, and we are doing transformation in the other method, and in the other method also we are accessing that object. Okay, with this reference, same object is being accessed. Okay, so with because of that, what we are doing, because of that, uh, whatever transformation is happening in this reverse method will reflect in the first method as well. So in that case, int n is equal to list dot size will be happening. Okay, now what will happen, we'll call this mid, and mid is the, since this is a perfect binary tree, so at any level the number of, you know, the number of nodes will be double the number of nodes in the previous level, and mid will be the actual, you know, total number of nodes by 2, and we'll be exchanging the nodes in the first half with the second half. So the mid will be actually the middle value, and then our loop will be, the loop which will be entering is like this, and then like this, and so tree node from last will be list dot get n minus 1 is the last index, and minus 1, so pairing will be, you know, tree node current is equal to list dot get of I. So these are the two pair nodes which will be exchanged, and to exchange we'll be using the same logic. Last dot get last dot val. Okay, and then last dot val is equal to current dot val, and then in the current dot val will be storing the temp. Okay, so we need not return anything. So we have done, and let me just run this. So there is some mistake. Okay, so mistake is output 235, so it means that the reversal is not happening. So reversal is not happening, it means that our logic to check level 0, level 1, okay, and then it should be doing here level 1, yeah, level and 1, this is correct, is equal to 1, it should return the value of so let's, you know, check here what is the content of this list and the level. List content is and the level is, so for this example thou will be getting, you know, some not the exact this 13 and 11, it will be showing some, you know, memory address, but there should be two references for the second, you know, output, and the level should be 1. So if that we are getting, then our logic is correct. Let me check. So in this second case, okay, we are not getting anything. Yeah, level 2 we should not get anything, so level 1 is correct. Okay, so maybe in our reversal logic we are not doing the correct thing. Last val n minus 1 minus I. Okay, so Let me check what is the value that is being shown here in the last and the current. The value in the last is last.val, and the value in the current is current.val. Okay, so let's see the output that we are getting here. The value in the last is 13 and the current is 13. How come, man? Okay, why it is last is 13 and current is also 13? How come? So list that is getting passed is same reference is there. Why? Oh, node dot right we should pass na. Okay, so our job is done now. We'll remove this. Okay, we'll pass this. Okay, so let's submit this. So this is the way which I solved this problem in the first instance. Okay, so I hope these two methods are clear to you. With this I would like to end this video. Thanking you. Happy coding. Best wishes.